All right, so let's get started. So today I want to finish up something I mentioned at the end of last time, namely I want to prove this theorem of Serre, which was kind of a complex analog of the Weil conjectures, and then I'll get started with the actual content of the course. So I'll remind you what Atomorphisms are. If you haven't seen that, I'll give some details. And then I'll also start defining the Étale topology, and hopefully we'll even get to kind of partial definition of what Étale homology actually is already. All right, so let's talk about this theorem of Serre. So what does the theorem say? It says that if you have a smooth projective variety over the complex numbers and an endomorphism of that, which I'm calling F, it's supposed to remind you of Frobenius, with the following property: if you take the cohomology class of a hyperplane section, so that's just the intersection with a hyperplane in projective space, what this endomorphism does to that class is it multiplies it by Q, where Q is some positive integer. And then the theorem that Serre proved is that in this situation, the eigenvalues of F acting on the cohomology of your variety in degree I will have absolute value Q to the I over 2, and it's the same Q as shows up here. So why am I proving this theorem? So this is a complex analog of the Riemann hypothesis and the Weil conjectures. Later on, when we prove the Riemann hypothesis for varieties over finite fields, we'll prove it by showing that Frobenius acts like this on the Étale cohomology of a variety. And what I want to do is convince you that that there's like a reason this is true. So it's true because of some special behaviors of the cohomology of varieties, like behaviors which don't happen for like random topological spaces. So just a word of warning. I mean, the proof is not going to look at all like Bilinear's proof of the Riemann hypothesis for varieties over finite fields. Like you'll see some shadows of it, like it kind of inspires that proof, but there's a lot of things we're going to use about complex varieties that we actually still don't know are true for varieties over finite fields, or that we only know are true because of the Weil conjectures.
So you can ask.
Is there a question, Arvind?
Yeah, what are elements of H2 exactly? Because I've never actually worked with this before.
I'm sorry, can you say that again?
So what is H2 parameterized, or what are elements of H2?
Oh, this thing. So this is singular cohomology. So have you seen this before?
So I had not seen it prior to this like last class. So
I see. So if you want, the Z here is not really necessary. You could put C. And then what these things are is you take C infinity differential forms. So it's just Theorem of Homology. So it's differential forms whose exterior derivative is 0, modulo differential forms which are in the image of D. Is that familiar?
Regretfully, I haven't taken differential. I mean, I've never studied differential forms.
Oh,
I mean, is there
right,
a simple description maybe of what an element looks like?
It's kind of complicated. So maybe what I'll say is that they're homotopian variants of a topological space, and in the case that space is a variety, they have some extra structure I'll define. But maybe it isn't actually going to be important what they actually are. They're just some variants. Is that okay?
Yeah, that's fine. Thanks.
And then you'll learn. Later in the course we'll do Étale cohomology, which is going to be a version of it. So you'll learn about all these properties in some other setting. Okay, so let me kind of tell you the properties we're going to need. So first of all, there's a cup product. So facts. So there's a cup product map, which I'm going to call L, from HI of X. Let's use complex coefficients now, to HI plus 2 of XC. And what it does is it sends the class alpha to the alpha cup with the hyperplane class. Okay, so this is, again, if you haven't seen this before, it's okay. All it's saying is that these groups, when you sum them all together, are an algebra, and I have an element in them, so I can multiply by that element. Okay, and then the part of the content, so the relative in content for us of the Hardy-Lefschetz theorem. Sorry, RSRUM, we're getting a little bit of feedback from your microphone. So part of the content of the Hardy-Lefschetz theorem is that each of these cohomology groups decomposes canonically into the image of L plus some other piece. which I'll call Hj prim. Okay, so that's called the primitive cohomology. So when I say canonically, I mean that canonical choice depends on this hyperplane class, but once you've chosen the hyperplane class, it's a canonical direct sum decomposition. Okay, this Hj prim behaves well with respect to the underlying structures on these cohomologies. So these cohomologies have a Hodge structure, which means they're the direct sum canonically of some subspaces called HPQ. And this Hj prim is also going to decompose canonically as into these pieces called HJQ prims, where here E plus Q equals J. And again, if you haven't seen this, it doesn't matter. I'm just describing some structure on cohomology, which is like very non-trivial to prove, but it's sort of well known at this point. Okay, and then finally there's the Hodge index theorem. Which says that if you have alpha and beta in HK X prim, so this primitive cohomology, then there's a natural pairing between alpha and beta, which is given by the following thing. So you take I to the K, so that's I meaning a square root of -1, times the integral over X of alpha wedge beta bar. So this is something in H2K. We can integrate something in Hn. So we're gonna wedge with this this class of the hyperplane n minus k times. So this is now a top form on the manifold. So that's something you can integrate. Okay, and then the theorem is that this is definite as a bilinear form on each HPQ prim. Okay, so we'll put together, like, what do all these theorems say? They say that cohomology breaks up into a bunch of pieces. So this piece comes from lower degree cohomology, so maybe we can control it inductively. And then this piece is broken up into pieces which have a canonical bilinear form on them, and that bilinear form is definite. Meaning if you pair something with itself, you get a non-zero number, unless the thing you started with was already 0. Okay, are there any questions about this? So I know if you haven't seen this before, this is a lot of stuff, but what you should take away is that these cohomology groups of a complex projective variety have some really nice extra structure on them. And we're going to use that to prove this analog of the Riemann hypothesis. Okay, so are there any questions? All right, so now let me sketch the proof of Serre's analog of the Riemann hypothesis. So just a reminder, what do we want? We want to show that the eigenvalues of pulling back by this endomorphism F on let's say HK of X with complex coefficients, so that this special vector space have absolute value Q to the I over 2, or sorry, Q to the K over 2. And let me remind you, Q was the number that a hyperplane class is multiplied by. Okay, cool. So first of all, it suffices to do this for HK prim, so this primitive part. So that was this kind of canonical orthogonal complement to the image of cut prodding thing with the hyperplane class. So can anyone tell me why that's true? So it just follows from the kind of formal properties of what I've described so far. All right, so let's do it. So well, if we can do it on, so saying that it suffices to do it for the primitive part says that it's easy to do it for ML. So why is that? Well, if you have an eigenvector alpha in hk minus 2 of xc, so by induction on k, you can assume the eigenvalue as absolute value q to the k minus 2 over 2. Right? So now if you take alpha cup this hyperplane class, well, what happens when you pull it back through F? You get F star alpha cup F star this hyperplane class, and that's the eigenvalue times alpha cup with Q times the hyperplane class by assumption on what F does to H, and that's Q lambda times alpha cup the hyperplane class. So that shows that this is again an eigenvector, and the eigenvalue is Q times lambda, and then this is absolute value Q to the K over 2, which is what we wanted. Okay. Are there any questions about that? So we just proved the statement for the image of this operator L given by cupping with the hyperplane class. All right. So now let's do it. Let's do it for the primitive part. So let's let
Daniel, what about the basis step of the induction? I guess for k equals 0 and 1.
Yeah, so for k equals 0 and 1, the whole thing is going to be primitive because this ML is 0. So we haven't done that yet. Yeah, does that answer your question?
Yes.
Yeah, great. Yeah, so let's do it for the primitive part. So let's let alpha in hk prim be an F star eigenvector. And let's consider what happens when we pair F star alpha with itself. And just to remind you, the pairing was this kind of funny object. And let me actually make a further assumption actually. So F star preserves these special subspaces HPQ. So we can actually assume that alpha lives in some HPQ prim with some PQ such that P plus Q equals K. Okay, so this is a bilinear form, so or a sesquilinear form or whatever it's called. So on one hand, this thing is just going to equal the absolute value of our eigenvector times alpha comma alpha. Sorry, this should be squared. Right, that's just because on the left-hand side you pull out a lambda, and on the right-hand side you pull out a lambda bar. So here lambda is the eigenvalue. Okay, so let's actually compute what this right-hand side is. So just from the definition, it's I to the k times the integral of F star alpha wedge F star alpha bar wedge h to the n minus k. So remember, this is something we did to wedge up to the top degree cohomology, so we can integrate. All right, so this almost looks like F star of alpha wedge alpha bar wedge h to the n minus k. So let's make it look like that even more. So the only difference between this and F star alpha wedge alpha bar wedge h to the n minus k is a factor of q to the n over n minus k. So let's divide by it. So we get I to the k for q to the n minus k, and then this is the F star of what you would normally take when you write down this pairing. Okay, so this is a top degree form. This is in h2n of xc. And it's a little exercise, for example, using the Lefschetz hyperplane theorem or Poincare duality. that f star acts on this thing via q to the n. So what that means is that we can write this as q, well, we can just pull out that q to the n. So we q to the n I to the k, or q to the n minus k times the integral of alpha wedge alpha bar wedge h to the n minus k. Okay, and now let's just simplify that. So this I to the k times this integral is just the pairing of alpha and alpha bar. So we just get q to the k times alpha and alpha. All right, so now we're done as long as we know that this thing is non-zero, right? Because if alpha is not equal to 0, we get that the absolute value of lambda squared is q to the k, and that tells us that the absolute value of lambda is q to the k over 2. So that's what we wanted to prove. So why is alpha paired with itself non-zero? Well, this is exactly the statement of the Hodge index theorem. Namely that this pairing is non-degenerate, or is definite, sorry, on the HPQ grounds. Okay, so I know that was a lot of stuff. The slogan you should take away from here, and I think it's very cool. It's just that the sort of structures on cohomology like imply this complex analog of the Riemann hypothesis, and we're going to want to prove something like that for varieties of our finite field once we define a cohomology theory. And that's going to be hard. I mean, and it's something that actually Deligne doesn't quite succeed in doing. Like, there's certainly no analog of this Hodge decomposition, and we don't know the analog of the Hodge index theorem, but we'll still see shadows of those structures in the actual proof. Okay, so that's the end of the introduction to the course. I know that was a kind of a fancy introduction, but I think it's worth seeing this proof for culture, because it's like one of the big motivating things that's going to motivate what happens in the rest of the course. So in a couple minutes, I'm going to start defining Étale morphisms and the Étale topology and stuff. But before I do that, are there any questions?
I have a brief question, I guess. If I relax any of the hypotheses on X, say, so maybe I don't assume it's smooth or something, is it false? Or
yeah, so it's false, but it's also a little hard to state. So for example, you have to have at least enough hypotheses to have to be able to define a cycle class of a hyperplane section, which won't be satisfied in total generality. There are versions that will be true. So there's other kinds of cohomology theories, like there's intersection homology where something like this is going to be true. In general, you can make a statement for arbitrary varieties where if you look at the eigenvalues of an endomorphism satisfying some hypothesis, which is maybe too technical to state, you'll get the absolute values of the eigenvalues are q to a half integer, but that half integer won't always be half of the cohomological degree. So this is closely related to the theory of weights. And Eric asks in the chat, should you go to Hartshorn if you're not following? So this is about to get much easier. So that was something that was sort of motivation, and I was giving some description of some stuff in complex geometry. And now I'm going to actually go back to the theory of schemes and introduce some much more fundamental stuff. So Eric, if you're not quite following, I think you shouldn't worry, and you should stick with it for a little bit and see how you feel. All right. Are there any other questions? All right, so if not, let's get to the meat of the course. So I want to talk about Atomorphisms. All right, so So this is a property of morphisms of schemes. So if you're familiar with Hartshorn, hopefully you've seen this, but if not, I'm gonna give a review. So suppose f from x to y is a morphism of schemes. So this is what it means to be étale. So we say that f is étale if it's locally a finite presentation. It's flat and it's unramified. So if you don't remember what unramified means, I'll tell you in a second. So actually, can anyone tell me what it means for a morphism to be unramified? So there's a bunch of equivalent definitions. So if anyone wants to jump in. Okay, so one definition is that the relative Kähler differentials are 0. But there's an equivalent definition which is that all residue field extensions are separable. Meaning if you have a point on y and a point above it in x, then if you look at the residue fields of those points, you get a field extension, and you want that field extension to be separable. Okay, so there's a bunch of equivalent definitions of étale, and I'll tell you some of them, and then we'll discuss some examples and properties of étale morphisms.
Wait, but that's not quite étale, right? Don't you also need that you don't have like multiple points over a single?
I'm sorry?
Don't you also need you don't have like multiple points over a single point, as in like?
What do you mean by that?
Yeah, what do I mean? I mean like nilpotents in the local ring. What am I trying to say?
I think if I understand correctly what you're saying, that's going to be ruled out by flat, but it's certainly possible for x and y to have nilpotents. They just somehow have to have the same amount of nilpotents.
No, I'm not saying it correctly. I mean, like if you just look at just x goes to x squared on the affine line.
Yeah, that's not étale, but it won't be unramified.
Right, but it satisfies your condition that the residue field extensions are separable.
Oh, I see what you're saying. Yeah. So when I say residue field extensions are separable, what I mean is you take the maximal ideal of the point downstairs and then look at what's cut out by it upstairs. So that won't be a field in your example. So maybe I haven't been exactly precise about what I mean by this, but so if you want a precise definition, you can take this. Does that answer your question, Arvin?
Yeah, thanks.
Yeah. All right. So here's some equivalent definitions. So one is that it's smooth of relative dimension 0. So another definition, it's one I like, is that it's locally finite presentation and formally étale. So let me remind you what that means. So what is the definition of formally étale? So we've got a morphism x to y. And suppose we have a map from spec A, where A is some ring, into Y, and spec A mod I into X. And here I is going to be a nilpotent ideal. So then formally étale means that there's a unique lift, like this. Okay, so let's talk about what picture this is supposed to be capturing. So what you're supposed to imagine is that X is a covering space of Y, or at least locally, this map you're supposed to imagine is a local isomorphism. So let me draw a picture. So here's locally on X and Y. Well, here we have spec A, which maybe looks like it has some nilpotent thickening because the side at the end is 0. And then we have a map from our subscheme, A mod I, which we're supposed to think is maybe the reduced scheme or something. And this is saying that if you have these little tangent vectors over here, you can lift them in a unique way upstairs. So that's saying that at the level of, that's some sense, in some sense in which this literally is a local isomorphism. I mean, it's actually not a local isomorphism, and we'll see some examples where it's not, but from the point of view of nilpotence, it is. Is that is that picture at least reasonably intuitive? Okay, and let me give one more equivalent definition, which is that it's locally standard Étale. So in particular, it's locally going to look like kind of the fundamental example of an Étale morphism. So let me say what that is. So what does that mean? That means that for each x in x, if we set y equal to f of x, then there exists a u containing little x, so this is inside of capital X, and a v containing little y, such that f of u is contained in v. And so that these u and v have very special forms. So v is going to be spec r for some ring R, and u will be spec of R adjoined to one variable, localized at some polynomial h, and modulo some polynomial g, such that the derivative of g is a unit in R adjoint x, localized at h, and g is monic. Okay, so what is this saying? Can anyone try to turn this weird description into words? So here's the picture. So this is spec R. Spec R adjoint x is just R times an affine space. So this is spec R adjoint x. So what happens when we mod out by some polynomial g in x?
You get a curve in that plane.
I'm sorry, yeah, so that gives you a curve. So modding out by g, so this cuts out the roots of g, right? Great. Okay, and then what does the condition that g, so inverting h just deletes some locus, namely where h vanishes. And what does this condition that the derivative of g is a unit mean? So it means that if we look at the fibers, g has no double roots in those fibers, right? So that's saying that this locus that we deleted passes through all the double roots of g. So what you're supposed to think, so the slogan is that g prime being a unit means that g has no double roots in the fibers. Okay, so the exercise you should do is that check that standard Atomorphisms are Étale. Okay, and then try to prove or read the proof of this statement that Étale morphisms are all locally standard Étale in this sense. So Arvind asks, can't we always choose H to remove the locus of double roots? And you can. I mean, that's somehow the content of Étale morphisms being locally standard Étale. But if you try to, so maybe Arvind is asking why every morphism isn't Étale. And the reason is that you need to be able to choose this V containing this U containing any given point X, right? So what if X was one of those double roots? Then you wouldn't be able to do that, right? So the statement that Étale morphisms are locally standard Étale is the statement that you can do this. So you can choose an H to invert without deleting any of your points. Does that answer your question, Arvind?
Yeah, thanks. That's what I'm saying.
Great. Cool. Okay, so let's do some examples. Okay, so can anyone give me an example of a Étale morphism? So Wanlin says an isogeny. So can you say a little bit more? So not every isogeny is Étale. So I assume you mean an isogeny. Yeah, okay, so multiplication by 2 on an elliptic curve, and then Arvind says in characteristic 0. Yeah, so multiplication by 2 on an elliptic curve won't be Étale in characteristic 2. So here's some examples. Multiplication by n on an elliptic curve. And this is if the integer n is invertible in the base. So for example, in your field. So let's do a slightly simpler example. So this of the same nature. So let's take GMs. This is the multiplicative group. It's spec of K, T inverse. And there's a map from GM to GM given by sending T to T to the N. And this is Étale if N is prime to the characteristic. Where as usual, I'm using the convention that that everything is prime to 0, which is maybe an unusual convention if you're used to everything dividing 0. Can anyone tell me why this is Étale? Well, I'll leave it to you as an exercise. That this is Étale. But the hint is that the derivative of T to the N is N times T to the N minus 1, and this is a unit. Right, and here you see why N has to be prime to the characteristic. All right, here's another example. Let's take GM. So remember, that's the affine line without the origin, spec of K, T inverse. Well, that maps in an obvious way into the affine line, right? Just via the inclusion of K of T into K of T inverse. Can anyone tell me why this is Étale? I see Arvind asks, are fibers in bijection with roots of unity? Yeah, so in this example, roots of unity act transitively on the, simply transitively on the fibers. So can anyone tell me why this example, just the inclusion of the affine line without the origin into the affine line, is Étale? So what do we have to check? So we have to check 3 things. So we have to check locally finite presentation, flat, and omega 1 of GM over A1, the Kähler differentials are 0. So is it locally finite presentation? Well, in this case, these are just affines, so we can check if it's finite presentation. So is this a finitely presented ring map? It's okay to just give me a thumbs up in the participants window if you want. Yeah, so one asks if all open embeddings are Étale, and yes, so we're going to prove that. Yeah, so okay, so this is locally finite presentation because look, I just gave you a finite presentation. All you have to do is adjoin an inverse of t that's adjoining one element. That's one relation. That's fine. Okay, it's flat because the risky open embeddings are flat, and omega 1 of GM over A1 is 0 because that's true for Zariski open embeddings. All right, so it's Étale, and in fact the proposition, which we just checked, and you should convince yourself that we checked it, is that any open immersion. Okay, can anyone give me an example of a Étale map which satisfies the following property? So example, I want so this example I gave you before of t goes to t to the n on GM is finite Étale, meaning this is a finite morphism. So can anyone give me a map of an example of an Étale morphism which is not finite onto its image? So here I gave you an example of an Étale morphism, which is a finite Étale morphism. Here I gave, meaning it's a finite morphism, which is also Étale. Here I gave you an example of an Étale morphism, which is not finite. This is not this KTT inverse is not a finitely generated extension of KT as a module, just as a ring, but it's finite onto its image. Its image is just itself. So can anyone give me an example of an Étale morphism which is not finite onto its image? So one says spec k to spec k bar. So that's not, or spec k bar to spec k. So that's not finitely presented, right? So it's not, doesn't quite work. I mean, depending on what k is. But I think if it is finitely presented, it's going to be actually finite. Anyone else? My hint is that maybe you can modify this example a little bit. So let me tell you the answer. So take GM, so that's the affine line without the origin, and also remove 1. And then this maps to GM again, just via the squaring map. And I'm going to assume that the characteristic of the ground field is not 2. So what's the picture? So here's GM, so it's the affine line without the origin. And well, the squaring map looks kind of like this. So at every point, there's 2 square roots, right? So this is the squaring map. But then I've also deleted one of the preimages of 1. So can anyone tell me why this is not a finite map?
It's not proper, maybe.
Yeah, so it's not proper, right? Because of this deleted point. So this map is an Étale surjection, but it's not proper, but not finite Étale. Okay, so sometimes people will tell you that Étale maps look like covering spaces, and that's true locally on the source, in some sense. I mean, for example, in a sense made formal by the criterion of formal Étaleness. But it's not true globally, and this is an example where you have something that doesn't really look like a covering space locally on the target. Okay, and this example is actually, I think, kind of important to keep in mind because Yeah, because often you'll see people kind of make arguments where they imagine that Étale maps are finite onto their image, and that's not always true. Okay, maybe let me just give you one more example along the lines of what one said. So if you have a finite separable field extension, that's when you apply spec to that gives you an Étale map. Okay, so let's do some non-examples. So can anyone give me an example of a map, a finite map, which is not Étale?
Are normalizations not Étale?
Well, they can be. So for example, if you normalize a normal ring, then you'll get the identity. But yeah, in general,
Yeah.
if you
How about like a singular curve or something?
Sure, that won't be Étale. So if you take the normalization, let me set x equal to be like spec kxy mod xy. So that's looks like that. Then the normalization of x to x is not Étale. Can anyone tell me why not? So it's not flat. That's one. So what about a finite flat map, which is not Étale? So Arvin kind of already gave me an example, I think, at the beginning when we were discussing what exactly it meant for residue field extensions to be separable. So if you take A1 to A1, the coordinate t goes to t squared. So that looks like this. So this is not Étale. Can anyone tell me why?
It's ramified at 0.
Yeah, so it's ramified at 0, so we can actually compute. So let's call this map F and compute the relative Kähler differentials. So what will it look like? It'll look like the Kähler differentials of A1 modulo the derivative of t squared, right? Which is 2 dt, 2 t dt. So that's k t dt mod 2 t dt. Okay, and 2 t dt doesn't generate this module, right? So this is going to be supported at t equals 0, and this is again if the characteristic is not 2. Great.
I guess going back to your examples, if you have the ring integers of a number field and you have an unramified extension of the field, then the ring integers up above is, or if you localize in an arbitrary extension at the ramification locus, then you'd be good.
Yeah, that's a great example. Yeah, so yeah, we don't have to work with varieties over a field, or you can work with, for example, ring of integers of a number field, and as sorry, is that Vapormorphisms?
Yes.
Yeah. So as Bob says, if you have an unramified extension, that gives you an Atomorphism when you apply spec to it, or if you invert so the primes, some primes containing the ramification locus, then you also get an Atomorphism. Okay. Can anyone give me an example of a morphism which is not Étale, which is finite, and such that it's a finite flat, and such that omega 1 x or y is not torsion. So here we found an example where this relative Kähler differentials was torsion. So my hint is that the same example almost works if I change one feature of it.
Change the dimension, maybe?
Well, so if I change the dimension, I think I'll still have that without changing the other crucial feature. I think I'll still have that, like, so for example, if I took A2, then you just get, and you know, you take one of the t goes to t squared, and t1 goes to t1 squared and t2 goes to t2 squared or something, then you get that the Kähler differentials are supported on the axes, right? Which is still torsion.
And you raise t to a higher power.
You could, but then I think you just get n times t to the n minus 1, so you'd still get something supported at 0, so it'd still be torsion. So what you can do is change the characteristic, right? So let's try an example. So let's try a1 goes to a1, where t goes to t to the p, and here this is some characteristic p. So I'm gonna suggestively call this map capital F. And what is omega 1f? So it's k join t dt modulo the derivative of a map, so d of t to the p. What's that? So that's d of t to the p is what? In characteristic p, what is the derivative of t to the p?
0.
0.
Yeah, so we just get k join t dt. Okay, and this is a line bundle. It's not a torsion sheet. Okay, great. So this map has a name. It's called relative Frobenius. And in general, if you look at sort of Frobenii, their Kähler differentials are going to be very big, which is something that you might not be used to. Like usually, if you have in characteristic 0, if you have a map of relative dimension 0, it's going to be generically Étale. It's flat. And then Kähler differentials will always be torsion. Okay, so let me give one more example, which is again kind of a generic example. So suppose I have f from affine M space to affine M space, and such a polynomial is, such a map is just given by M polynomials and M variables, right? So you can ask, where is f Étale? So f is Étale in a neighborhood of a point a1 through am if just the Jacobian is even. So if the determinant of dfi dxj evaluated at 1 through am is even. Okay, and this is something that's hopefully familiar from differential geometry. All right, let's take a 3-minute break, since I think we've been going for a while. We have what, like 25 minutes left in class, and then we'll continue. So if y'all want to just chat, I think it's nice to take a little break.
Can I ask a quick question in the meantime?
Yeah, sure.
It seems like unramified as a concept only makes sense for morphisms of relative dimension 0. Is that correct or no?
So yeah, so in general, okay, so relative dimension 0, how should I say this? I mean, it doesn't, I wouldn't say it only makes sense in that case, but if you're locally finite presentation, I think if you're not of relative dimension 0, you will never be unramified. Maybe that's what you're asking.
So you're saying, for instance, just
like the definition makes perfect sense, right? You can ask, like, is omega 1 x over y 0? Yeah, here we go. Yeah, like this, you can ask for a general morphism, right? You don't have to have relative dimension 0 to ask this.
Right.
But it just, you know, if you have something which is not relative dimension 0, this will never happen. With some exceptions. I mean, so this is only a good definition if you're locally finite presentation. And dimension in general only really makes sense with some conditions like that. So yeah.
Sorry, also, can you also give an example of a map that's locally a finite presentation but not a finite presentation? Because I can never think of these things.
Sure. You can take a point and take an infinite disjoint union of copies of that point mapping to the point. So locally on the source, it's just the identity, right? But it's not a finite presentation because it's very large. All right, Haiyang asks if flat and unramified implies finite type. Does flat and unramified imply? So I would only use the word unramified if you're in a locally finite presentation situation. And for me, finite type just means locally finite presentation.
Okay, and I'm reading Milner's textbook. It seems like in the textbook it says that it only requires flat and unramified for it to be Étale. I don't know whether.
Yeah, so that's because Milne is working in a less so he's always assuming all of his morphisms are finite type, and he's in a Noetherian setting, so there's only one real notion.
Okay.
Yeah, I'm trying to be a little bit careful about where I assume things. Like in a little bit, we're just going to be working for varieties over a field, but I'm trying not to assume that yet. Are there any other questions?
This is not a question.
Sorry. I'm a little confused about the field going to k-bar thing because I was thinking about a universal cover kind of scenario. Is that not Étale?
Well, so universal covers typically don't exist in algebraic geometry.
But the field go to k-bar should be an analog of.
Yeah, so it's not locally finite presentation. So
I see. So I should think that that's not Étale. Okay.
Yeah, it's there are notions. There's a notion of pro-Étale, which spec k-bar is, but yeah.
I see. Okay. Thanks. Okay, thanks.
This is a comment, not really a question. I've always heard that étale is a French word that means something like the appearance of the ocean in a certain way. I guess the waves rolling in smoothly. Do you have any remarks about that?
I was actually just reading about the etymology. So my understanding is that it actually is the same etymology as the word stale, like a loaf of bread. And it's something about hardness. But yeah, I don't know. I saw at least 2 stories about the etymology, and I don't know which one is correct. Yeah. Are there any other questions before we resume?
I don't know if this is relevant, but when we took Sheaf Cohomology with Dr. Alexei a couple of years ago, and he mentioned something about the E-space étale, but I think it was like a different concept.
Oh yeah, so if you have a sheaf on a topological space, there's something called the espace étalé, I think. And it's like an actual space living over the base, so that sections to that map are the same as sections to your sheaf. And I think there's some kind of relationship because that space, that map is a local isomorphism. It's supposed to be like what the étale, or local isomorphism on the source, which is supposed to be, in some cases at least, which is what the étale morphisms are trying to capture. But I think it's actually a different word. Like I think the espace étalé is another accent. All right, are there any other questions? All right, so let me just tell you some properties of atomorphisms, and I'm not going to prove them. You should read the proofs in the Stacks project or in Milne or in Hartshorn. So first of all, open emergence are Étale. So we already actually sketched the argument for this. 2 is that if you take the composition of atomorphisms are Étale, the compositions of atomorphisms. Okay, so again, what do you have to check? You have to check that local finite presentation, flatness, and unramifiedness are all preserved by compositions. So the only one that might be a little bit tricky is unramifiedness, and my hint is to use the exact sequence, like there's what do people call it, the cotangent exact sequence. Or omega 1 over y. Okay, next is the base change of an atomorphism is Étale. So So what do I mean by that? I mean that if you have x to y, étale, and a t mapping to y, and you take the fiber product, x times t over y. So if this is étale, then this is also étale. Okay, and then finally, there's a kind of 2 out of 3 property. So if you have phi comes opposed with psi, and also phi is, if these are both étale, this implies that psi is étale. Okay, and again, this is something you should do as an exercise. All right, are there any questions about that? Okay, and then finally, there's one more really important property I want to mention about atomorphisms, which again, hopefully you've seen before, but if not, I'm happy to talk more about it, which is that atomorphisms how should I say this? On varieties over an algebraically closed field induce isomorphisms on complete local rings at closed points. Okay, and here, again, this is something you should do as an exercise, but my hint is to use the criterion for formal atoms. So there's an evident map one way on local rings coming from just a map your atomorphism, and you have to produce another the inverse map using formal atoms. So Sophia asks if this is any 2 out of 3, and the answer is no. So it's really just this 2 out of 3 property. So it's actually two of the 3 2 out of 3. So one of them, this composition tells us that if phi and psi are étale, then this composition is étale. Then we also have this one. So if phi and the composition are étale, then psi is étale. But the other way, if psi is étale and the composition is étale, phi is not necessarily étale. And we should come up with an example. And my hint is that you can build an example by composing the various examples we've already discussed today. Great. Okay, and so why did I tell you this proposition? So the corollary of this proposition, and this is kind of an informal statement, is that any property that can be checked at the level of complete local rings as you know, there are many such properties. It is true for the source of an atomorphism if it's true for the target. And why is it? Well, you want to check it on the complete local rings on the source. Well, your map induces an isomorphism on complete local rings with complete local rings on the target, so you can just check it. All right. So that was our review of atomorphisms. We have about 15 minutes left. So maybe I'll ask if there are any questions, and then I'll start motivating what we'll talk about next time, which is the Étale topology and sort of a generalization of the notion of a topology in general. So are there any questions about what we've talked about? So Arvin asks, can we replace completion with henselization? And the answer is yes, but I'm not going to talk about henselization for a couple more class periods. Yeah, so maybe just as a preview of what we'll talk about, then so there's a notion of a local ring for the Zariski topology you're probably used to, like the local ring at a point of the scheme. Is a generalization of that notion to Étale setting, which is Henselization, which Arvin mentioned. So those will be the local rings for the topology we're going to talk about, and we'll talk about those in a couple class periods. Any other questions? All right, so let me start talking about sites. So this is going to be what we're going to use to define the so-called Étale topology and the notion of cohomology that goes with it. So these are going to be a generalization of topological spaces. Okay, and moreover, they'll let us generalize the notion of a sheaf. So what's the plan going to be? We're going to kind of come up with this generalization of a topological space. We'll generalize the notion of sheaf to that space, and then we'll define certain sheaves whose sheaf cohomology will be the kind of cohomology we're trying to capture. So for example, on a nice space, like a manifold, singular cohomology is just the same as the sheaf cohomology of the constant sheaf Z. And here we'll find some version of a sheaf where Étale cohomology, at least with like Z mod L to the n Z coefficients, is going to be the sheaf cohomology of the constant sheaf Z mod L to the n Z. Okay, so here's a question for y'all. So what do you need? So like what parts of the definition of a topological space do you need to define the notion of a sheaf? Any thoughts? Yeah, okay, so at least, so what is a sheaf? A sheaf is something that, yes, you need an open set. So you need a little bit more, right? A sheaf, well, so first of all, a sheaf is a pre-sheaf, and what does the pre-sheaf do? It associates to each open set a thing, let's say a set, if it's a set valued sheaf. And then if you have an inclusion of open sets, you get a map going the other way on the values of your sheaf, right? So you need a notion of open sets. And you need to know which sets are included in which other sets. So you need a notion of open sets and inclusions of open sets. So another way of saying that is you need a category of open sets. Okay, that's enough to define a pre-sheaf, right? So a pre-sheaf on a space X is just the same as a contravariant functor out of the category of open sets on X. So, okay, what is that category? The objects are open sets, and there's a morphism from U to V if U is contained in V, the unique morphism. And then composition just comes from the fact that inclusion is transitive. Okay, so actually, I want to make a remark on this, which is that this immediately tells you that the notion of a pre-sheaf on X doesn't know that much about the underlying topology of X, right? So all it knows is about this category. So for example, if you have two topological spaces, which are both given the coarsest possible topology, so like the one where the only open sets are the whole space and the empty set, the category of pre-sheaves on those spaces will just be the same, right? And why is that? It's because this category of open sets is the same. So this already tells you that to define a pre-sheaf, you don't need really a topology, you just need a category. Okay, what else do you need to define a sheaf? So somehow you have to make sense of the sheaf condition, right? So what kind of extra structure on the category of open sets do you need to define the sheaf condition? So let's actually write down the sheaf condition. So the sheaf condition two parts. It says that a section to a sheaf is determined by its values on the cover. And that so that's part one. And part two is that you can glue sections which agree on intersections. So I've underlined two words, namely, yeah, so Sophia says covers, and Mensela says intersections. Yeah, so those are the two things you need. Okay, so let's make sense of that. So you need a collection, you need a collection of collections of morphisms, so which we'll call covering families in a second, which are covers. So that's going to be some extra structure we put on this category. We're going to kind of remember which collections of maps. So in the topological setting, so like which collections of open subspaces of a given subspace cover that space. And then we're going to need a property, which is not a structure, namely that we're going to need the existence of certain fiber products. And which we're going to think of as intersections. And the motivation for kind of identifying fiber products with intersections is that if you have U and V are open subspaces of some space X, then the fiber product in, say, the category of topological spaces, or in this category of open sets of these two subsets over X is just their intersection. So this is kind of a categorical way of describing intersections. Okay, so I have about 6 more minutes, so I don't think I unfortunately have time to describe a growth and deep topology, but let me instead give you some examples, and then I'm going to kind of give a predefinition and some examples, and then we'll be rigorous about it next time. So this is kind of a predefinition of a growth and deep topology. So some people also call this a site. So maybe a little warning is that there's actually, I think, at least 3 different conventions I know of for what a site is and what a growth and deep topology is, and they're genuinely slightly different. And I'm going to choose the version that I think is actually, unfortunately, the least general, but also the easiest to work with. So what it is, it's going to be a category, C, with a collection of so-called covering families. So what's a covering family? It's just a bunch of morphisms. So here, X is an object and X alpha is another object, and I'm indexed by some set A, and I'm collecting a bunch of morphisms like this. So these are called covering families. You're supposed to think that if a set of morphisms is in this collection, then that set is that's saying that these X alphas cover X via these maps F alpha, such that some axioms are going to be satisfied. So I owe you the axioms. Since I only have 4 minutes, I'm not going to be able to write them down. And all they're trying to do is capture the properties of what a cover looks like in topology. But let me give you some examples. So an example is if you take X, a topological space, then I'll take C to be the category of open sets in X. So as a reminder that the category whose objects are open sets. whose morphisms are just given by inclusion. And I'll say that U alpha to U is a covering family if the U alpha cover U, meaning the union of U alpha is U. All right, let me give you two more slightly exotic examples. So let's suppose M is a manifold. Then I'm going to let C be the category of all M prime mapping to M. So it's the category of manifolds over M, such that F is locally on M prime an isomorphism. So these are smooth local homeomorphisms. And then I'm going to say that M alpha to M, so here all of these things are local homeomorphisms, so maybe they're open subsets of M, maybe they're covering spaces, whatever, is a covering family if the, so let me call these maps F alpha, if the union of the images of the F alphas is M. Okay, and here's an exercise. Well, okay, actually, I can't give you the exercise yet. I'll give you an exercise about these categories next time. Okay, and let me give you one more example. If X is a scheme, I'll let C, there's actually a name for it. I'll call it X Étale. It's a category. So it's the category of all Étale morphisms Y over X. So an object is a scheme Y with an Étale morphism from Y to X, and a morphism is a morphism over X. And then I'll call X alpha to X covering family if the exact same thing as before happens, if the union of the images of the F alpha is all of X. Okay, so this is going to be the fundamental object that we're going to study, this category with this set of covering families. And I'm out of time, but let me just define Étale cohomology for you. So we're going to define a notion of sheaves on this category. We're going to have a constant sheaf Z mod L to the n Z, and then Étale cohomology, at least with Z mod L to the n Z coefficients, is going to be the sheaf cohomology. And Arvind asks if the image of an Étale morphism is always open, and the answer is yes. And in fact, the image of a flat morphism is always open. All right, so we're out of time. I'll stick around for a few more minutes if people have questions, but I'm going to stop the recording now.